Hi everyone, we are going to now be doing an example for our chi-square statistic goodness of fit tests. Okay, so we're in chapter 11, section 1. In this example, we're looking at data from the 2000 census of all U.S. residents age 20 and older. 19.1% are in their 20s, 21.5% are in their 30s, 21.1% are in their 40s, and 15.5% are in their 50s, with 22.8% 60 and older. The table below shows you the age distribution for a sample of U.S. residents aged 20 and older. Members of the sample were chosen by randomly dialing landline telephone numbers. Remember, this is back from the year 2000, so not quite as strange. Do these data provide convincing evidence that the age distribution of people who answer landline telephone surveys is not the same as the age distribution of all U.S. residents? Okay, so we're still going to go through our 4-step process. That is the same as previous chapters, but it's going to look a little bit different. We're performing a hypothesis test here, but it's not exactly a hypothesis test, it's a chi-square test, okay? So what we want to do is we want to perform a test of the following hypotheses using alpha is equal to 0.05. We're going to be coming up with a p-value, and we need to have something to compare it to. So we always use an alpha of 0.05. So that's very similar to when we did significance testing. Now, when it comes to our null and our alternative hypotheses, we don't have just a mean or one proportion or even two proportions. There are 1, 2, 3, 4, 5 different categories here, right? We don't know what that's going to look like. So for writing our hypotheses, we're either going to say that it is what we expect it to be, or it's not the same as we expect it to be. So let's look at what that looks like for the null. Our null hypothesis says that the age distribution of people who answer landline telephone surveys is the same as the distribution of all U.S. residents. So, like we did in our Chapter 9 and Chapter 10, when we had our significance tests, our null was always an equal. So in this case, we want to say it's the same, meaning all the proportions are the same, all the counts are the same as what we would expect it to be. Now, the alternative here is going to be that it is not the same. So essentially the exact same thing we just wrote, but instead of saying it is the same, we're going to say that it's not the same. Our alternative is that the age distribution of people who answer landline telephone surveys is not the same as the distribution of all U.S. residents. Okay? And I gathered that from my question up here. Do the data provide convincing evidence that the distribution of people who answer landlines is not the same? So that's my alternative. That's what we're going to be testing here. Now, another way to write these hypotheses, you could write them using the proportions, right, up here. The only downside that is that if you said, oh, p sub 1 is 0.191 and p sub 2 is 0.215, etc., then you would have to go through and define all of those parameters, which can be a lot, right? There's only 1, 2, 3, 4, 5 here, but, I mean, it could be a lot. Then if you were to do it that way, your alternative wouldn't be that they're all not equal to, it would have to be that at least one is not what it says up here. So it's okay if some of them end up being what we expect, but not all of them being the same as what we're testing here for all alternative. Okay? All right, let's come up with a plan. Okay, let's come up with a plan. We're going to use, and this is where we say the method, right? Is it a t-interval? Is it a z-test? Is it for means? Is it for proportions? So we're going to use what's called a chi-square goodness of fit test if our conditions are met. Now, there are multiple types of chi-square tests. Goodness of fit is the first one we're learning about. So you do need to say not just general old chi-square, but it's a chi-square goodness of fit test. Right? We have 3 conditions, similar to when we did hypothesis testing. 2 of them are exactly the same as before, random condition and the independent condition. And then before we used to check for normal, it's going to be something different now. So the first one is our random, okay? In this instance, the data did come from a random sample of U.S. residents. So our random condition has been satisfied. Next would be our normal condition, but we're using chi-square. We don't need it to be normal, right? Chi-square is not normal. Normal is symmetric. Chi-square is skewed right. Normal has positive and negative values. Chi-square is only positive values. So in place of the normal condition, we are now checking for a large sample size, right? Checking for large counts. It's a similar concept to when we were doing proportions. We would do some multiplication and check to make sure that my values were at least 10. Large sample size here is going to be if my values, my expected counts, are at least 5. So how are we going to find our expected counts? Well, your total up here was 1048. And we're going to go through and find our proportions for each category and figure out the expected value, the expected counts. So 1048 times, and then if I go back up here, 19.1 for the 20s, so times 0.191, that gives us 200 let's go to 3 decimal places, 168, okay? So that takes care of the 20s. 1048 times 0.215. That gives us 225.32. 1048, let's see, 0.211 for the 40s. That gives us an expected count of 221.128. 1048 times, what was the 50s? The 50s was 15.5, so 0.155. That gives us 162.44. And then one more to check for 60 and older. 1048 times, what percent was that? 22.8, so 0.228. That gives us 238.944. Okay, so all our expected counts are at least 5. So that takes care of that. So these are all of our expected counts. We've got 1, 2, 3, 4, 5. Okay. If you want to see how they kind of compare, just before we get any further, it helps to write it. So this was our observed right here. Our expected, we can write just right here. So that gives us just a little comparison, right? It's okay if they're a little bit different. Some are higher, some are lower, and that's normal. Okay, that's to be expected. All right, last condition to check is independent. Okay. This comes from a sample. So again, since we're sampling without replacement, we need to check our 10% condition. Since we're sampling without replacement, we must assume that there are at least 10,048 U.S. residents who answer landline telephone surveys. Okay, so let's dive in to the actual calculations here. We need to calculate our test statistic. This is not new. but how we calculate it is, because our test statistic is no longer an x, or excuse me, it's no longer a z or a t, it is now a chi-square. The formula for calculating chi-square, you take each observed value, subtract your expected value, you square it, you divide it by your expected value, and then, you sum the whole thing up. That should be a sigma. Okay? So, looking at your data from above, we go through and we write at least 2 of them to start with, just so whoever's grading it has an idea of what it is that you're doing. You're going to let your calculator do most of the work, though. So, observed for the 20s, expected for the 20s, square it, divided by 200.168. Add that to, just do the next one, 186 minus 225.32. I'm just getting this from up here for the 30s. That would be squared and then divided by 225.32 plus ... All right, it's okay to do this because we can let our calculator figure it out for us. So what I'm going to do in my calculator is I'm going to go to my lists, make sure they're all cleared out. I'm going to put my observed in list 1 and my expected in list 2. Observed in list 1, expected in list 2. Now that my observed data are in my list 1 and my expected values are in list 2, I'm going to go to Stat, I'm going to go to Tests, and we are doing a chi-square goodness of fit test. So chi-square golf test, not just regular chi-square test. This is the next section. So it's going to ask you if your observed are in list 1 and your expected are in list 2. Yes. Degrees of freedom here, we forgot to mention, since there were 1, 2, 3, 4, 5 categories, my degrees of freedom is 1 minus that. So my degrees of freedom would be 4. Go down and calculate it. And we get a chi-square value of about 48.17. So that's pretty large. Right? Chi-square value tells you on average how far your observed are from what your expected would be. And then it gives us our p-value right there. But if, for instance, you didn't calculate this in your calculator and you did it all by hand, to get your p-value, we want to know the probability that your chi-square value is greater than 48.17. It's always going to be a greater than since it's a right-tailed distribution, right-skewed, I should say. So there's also a chi-square CDF function in your calculator. Just pick some really, really, really big number. Use your degrees of freedom. And looking at this, it says, oh, you can't see that. It says my p-value is 8.6. That's not possible. P-value stands for probability. Oh, look at the end. This means there's like 9 zeros after your decimal place. So it's a really, 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 really small number. So I'm going to say that my p-value is basically 0. It's really small. Okay? So since my p-value is so small, we're going to be rejecting our null hypothesis, which means we have convincing evidence to accept our alternative. Since our p-value is less than our alpha, we reject our null. We have convincing evidence that the age distribution of people who answer landline telephone surveys is not the same as the age distribution of all residents. Okay? All right, the next example comes from a very awesome book called Outliers by Malcolm Gladwell. I want you to try that example on your own. So complete that example on your own, and then at least do part A. Part B we'll talk about as well. And then we will check that either in another video or by looking at an answer key in class.